Last but not least, we're going to look at the next chapter. It's chapter 16, and talk a little bit about regression. So, regression. Actually, I want to share a few real-world examples with you first on what regression is. Regression is the business of trying to use a variable. Simple linear regression is trying to use one variable to try to predict another variable. For example, let's say, for the sake of example, that I was trying to predict your success in college. Do you remember what they did to you in high school to try to see if you can be successful in college? They probably gave you the SAT or the ACT test. And the idea is, does SAT or ACT predict success or GPA in college? Well, hopefully the SAT company collected enough data to show that was indeed the case. And actually, more recent statistics for that have not shown that to be the case. Many people can be very successful in college without necessarily doing well on the SATs. But if you believe that SAT is predictive of college success, operationally defined as maybe your GPA, your first year, then SAT would be used for regression. You would use SAT to predict GPA after the first year of college. So regression is the business of using one variable to predict another. Let's say that we were doing the example of, what else would be good? How about a heart attack? Would it be good to be able to predict who's going to have a heart attack? Hopefully, yes. Maybe the idea would be you could collect data from people and you can look at their cholesterol intake and maybe use cholesterol intake to predict who's going to have a heart attack. So in that situation, it would be a simple linear regression looking at one variable to predict another. Now, if you thought that the ability to predict who's going to have a heart attack really depended on a couple of variables, that would be a slightly different situation. That's what we would call multiple regression. In multiple regression, we try to collect a few predictor variables and try to use them to predict a key dependent variable, which in this case is who's getting a heart attack. So simple linear regression, we try to use one variable to predict a second one. In multiple regression, we try to use a couple of variables, maybe the real important ones, to predict one DV as well. The example I wanted to go over was actually the example from the last lectures that we had, the idea of BMI, using BMI to predict snoring episodes and apnea. Do you think somebody who's a sleep medicine person would want to collect BMI information to try to predict who's going to have sleep apnea? The answer there would be yes, they would. So you can do regression. It's actually related a bit to correlation. Once again, if you look on this page, it starts with a scatter plot. So I'm going to go over some general information here with you and see what we can do. So in number one, for Roman numeral 2 regression, using one variable to predict another, this would be simple linear regression because we're trying to use BMI to predict snoring episodes. If I take that data that I started the lecture with on BMI and snoring episodes, I could put all that data into an SPSS program, into a stat program, and then I would actually get information that's in the table in B, the best fitting line equation. So I'm going to ask that you write a few notes on this so that you make sure you get it down. The idea here would be, if you look at that messy screen, that model in that table, you can see that it shows you variable 00001, and then it says 6.25, and it's got a negative 184. You can round that to 185. So the way you would do that is, and it says the dependent variable is variable 00002. So what you need to get from this screen is what we call the regression equation, the best fitting line equation. And the idea is, if you look at letter B, and just take some notes on this, I'll clarify it more next week, y hat, you can put a little sign over the y, is the predicted y value. And here, the predicted y value is equal to 6.25x minus 185. That is the best fitting line equation from that silly screen right above. So the idea there is, what does all this mean once again? The way that you would work with that equation is if you go down right below it, and you just kind of have to follow my recipe here. If you start with a BMI of 30, remember that was actually in the data set at the beginning. If you put the BMI of 30 in there, then 30x stands for the BMI. So you would do 30 times 6.25. So if you have a calculator, do 30 times 6.25. Let me see if I have my calculator here. I did a few minutes ago. And if you put that in, 30 times 6.25, and then you subtract 185, then you will actually get a result. Where did I put that thing? Here we go. Sorry about the delay. 30 times 6.2. Screwed it up. 30 times 6.25. That result is 187.5. So if you put a 30 into that equation, the predicted y hat value would actually be 187. Well, it comes out to 187.5. Then you subtract the 185 that was in there as the constant. So your predicted number of snoring episodes would be 2.5, because 187.5 minus 185, the predicted number of snoring episodes would be 2.5. And then what you would do with that is you would actually see that the actual number of snoring episodes was 10. So the amount of error with that was actually 7.5. So the idea is you put the number in, the BMI that you got, into the equation, and then you compare it to the actual number of snoring episodes. So what I would like you to do, and I'll explain this more next week, is do the math for each of the 5 numbers. We've already put the 30 in, and we got the predicted snoring episodes of 2.5. So what I'd like you to do is take the other 4 values and figure out what the predicted number of snoring episodes will be. And that's all you need to do. You don't need to calculate the error or the error squared. Just try doing that, and I'll explain more about this next week. So that is that screen. Let's continue on. And if you look at the final 2 screens, I'm just going to try to point out some important things for you. With C, the model summary, the key number, and I've put it in boldface, is what's called the adjusted R squared. The adjusted R squared here is 0.784. And you can actually do a little real-world statement from this, and you want to write this down. The adjusted R squared is given a name. It's called the coefficient of determination. This is in the chapter on regression. It's called the coefficient of determination. And what that 0.784 says is the following. It says to you that if I know BMI, I can account for 78.4% of the variability in snoring episodes. If I know BMI, I can account for 78% of the variability in snoring episodes. Does that sound like a good thing? If I know one variable, I can account for 78% of the variability in the other variable? The answer would hopefully be yes. That if I know one variable and I can account for 78% of the variability in the other one, that's a lot. And the final screen, the ANOVA screen, actually shows you that that 78%, where it has significance, is statistically significant. So the final screen on the ANOVA basically says that that 78% is significant. And the way you would write that out with the ANOVA screen, you would write F, and then in parentheses 1, 3 equals 15.51, P equals 0.029. So this screen would say that the amount, the 78%, that if I know BMI, I can account for 78% of the variability in snoring episodes. It's saying that that 78% is significant. So I know I've covered quite a bit here. We'll cover more of this next week to kind of fill in the gaps, but let me summarize what I've covered with regression. Regression is the business of using one variable in simple linear regression to predict another variable. And in this case, it's using BMI to predict snoring episodes, my operational definition of sleep apnea. Multiple regression is where you use a couple of variables to predict a DV. So if you were trying to predict heart attack, you might look at cholesterol levels, you might look at weight, you might look at type A personality, you might put a couple of variables in to try to predict another one. With multiple regression, we come up with what's called a best fitting line equation. And in B, you can see that you put the numbers in that you get a printout. And so if you look at that, the predicted Y value, Y hat it's called, equals 6.25x minus 185. That's the 184.75 rounded up. So that is the best fitting line equation. And what I've asked you to do is to take the BMIs that are in there and see if you can put that information in to predict what should happen to the actual snoring episodes and write those 5 numbers in there. And then next week we'll pick it up with that information. So you get a best fitting line equation. The model summary, C, it's called the coefficient of determination. If you know BMI, you can account for 78% of the variability in snoring frequency. So that's a lot. That's one variable that accounts for 78% out of 100. And the final screen says that that is a significant amount. F of 1 and 3 equals 15, P equals 0.029. So what I'd ask you to do for class next week is just take notes on this information, try to create a good outline, post this before the class, print this out and bring this in because I'll go over this in class and hopefully you'll have some questions to ask me. We'll fill all this in and then we'll go on with the lesson plan. Thank you all very much. Bye.